promised, here's the extra video for the last example of graphing a polynomial function that we didn't quite get to the Friday before spring break. So here we have this polynomial function. We're going to use our set of steps in order to get a graph. And remember, the first step is to check for symmetry. To check for symmetry, we take our original function, it's named g, and we plug negative x into it and we see what happens. So what we are going to end up with is the following. Negative x quantity cubed plus negative x squared minus 5 times negative x, and then plus 3 on the end. And then we'll go through and simplify, and we'll see what happens to the sign on each of our terms. So if you cube a negative, it's still negative, so we have negative x cubed here. If you square a negative, it becomes positive, so this is plus x squared. A negative times a negative makes plus 5x on this term, and then we have a plus 3 on the end. And we're going to compare this with our original function up on over here, and we're going to see basically what happened to the signs of each term. So we can observe that the sign on the x cubed term, the first term there, that changed, whereas the sign on the second term did not. It stayed the same. And that's enough for me to say that this is neither going to be an even or an odd function. Remember, for an even function, you should get the exact same thing as the original, and for an odd function, all the signs on all your terms need to change. Since we did a little bit of both, this is going to be neither. The next thing we're going to do is tackle figuring out what our intercepts are. Remember, for x-intercepts, we set our entire function equal to 0, and then we try to solve for x. In this case, we can see that we have a polynomial function, and it doesn't look like this is going to factor by grouping just by first glimpse. I could take an x squared out of these two terms, that'll leave behind x plus 1, but there's not really much I can take out of here, and so that's not going to work for me. That means I have no choice but to fall back on the stuff we've been talking about since section 2.3. I can use my rational zeros theorem to identify my possible zeros, and I can take it from there. So I'm going to begin by taking the factors of my constant term, 3, and dividing them by the factors of my leading coefficient. Now, there isn't an obvious number out front of the x cubed, but we can assume that there is a leading coefficient of 1 there, and that allows me to say the following. So since my leading coefficient is 1, I'm going to be dividing by plus or minus 1. And since my constant term is 3, the factors are 3 are 1 and 3, so I have a plus or minus 1 and a plus or minus 3 up here. Dividing 1 by 1 gives me 1, so I have plus or minus 1. And dividing 3 by 1 also gives me 3, and so I have plus or minus 3. So there are 4 possibilities for our possible rational zeros, and we'll just try each one of these until we find one that works. And we'll do that by using synthetic division. So I'll set that up. Here's my synthetic division box, and I'm just going to take one of these factors. It doesn't matter which one. I'm just going to choose one and start with it and see what happens. So let's say we choose 1 to be that value, and then we're going to list out our coefficients from this polynomial up here. Those are 1, 1, negative 5, and 3. Here's my remainder box, and we'll just proceed. First entry here is 0. We add. Bring down the 1. 1 times 1 gives me 1. 1 plus 1 gives me 2. 2 times 1 gives me 2. And 2 minus 5 is negative 3. And it looks like we're about to get lucky. Negative 3 times 1 is negative 3. And on the first phi, we found something that gives me a remainder of 0. So what this means is, well, remember, this guy right here is our c value. And because our remainder of 0, we have that x minus c, which happens to be x minus 1, is a factor. And more than that, we have that this right here basically are the coefficients of our quotient polynomial. And that's going to help me for the following reason. We're going to end up taking our original polynomial equation up here, and then I'll just carry it onto the next page, and I'll now be able to factor it into x minus 1, coming from here, times the quotient polynomial associated with this. And that quotient polynomial is, of course, x squared plus 2x minus 3. Now that we've managed to factor this, we can take a look at the quadratic part and see if we can break it down any further. We have x minus 1 times, and let's see if we can factor this. It looks like x plus 3x minus 1 will do. And here we have the factored form of this equation. So we can take each of these factors and set them equal to 0. So I'm going to have x minus 1 set equal to 0. So x equals 1 is one possibility. And from this factor, I have x plus 3 equals 0. And so x equals negative 3. So this means that I have two x-intercepts, and my x-intercepts are the ordered pairs 1, 0 and negative 3, 0. In addition to this, we have that the multiplicity on x equals 1 is going to be 2, because there were two copies of this in the factorization up here. And we have that the multiplicity on this one is 1, because there's only a single copy of the factor that it came from. So it says multiplicity 1. And so this guy is an even multiplicity. This guy is an odd multiplicity. And so we can reach the conclusion that at the x-intercept 1, 0, where we had multiplicity 1, we are going to cross through the x-axis there. While at negative 3, 0, because the multiplicity associated with that is 2, which is even, we are going to touch and turn at that particular x-intercept. So here we have the touch and turn bit. And there we go. We've done part 2 of this process. For the third part, we need to check out our end behavior, which requires the leading coefficient test. So we need to know our leading coefficient, which I always abbreviate LC, and we also need to know our degree. Our degree is 3. And our leading coefficient, as we mentioned earlier, is the number out in front of the x cubed term, so that is going to be 1. So specifically here, we have a leading coefficient that is positive, together with a degree that is odd, and that tells us that the ends of our function are basically going to behave like normal x cubed does. And so this end is going to go down, that end is going to go up. Or the alternate way to write this is the following. So we can say that as x gets really big, so as it goes towards positive infinity, or in other words, as we head to the right forever, so here's us heading to the right forever, my y values are going up forever as we do that, so as x approaches infinity, y is going up, so it's heading towards positive infinity. Similarly, if we go to the left forever, so if we head in this direction, our y values are going down. So as x heads towards negative infinity, y is heading towards negative infinity. So this is an alternate notation for this, and it just summarizes our end behavior for this particular function. The last thing I'm going to do is figure out what the y-intercept is, and that's going to come from plugging in 0 to our original function. If you've forgotten what that is, it's hanging out right here. And g of 0, well, we just plug in 0 for every x. We'll get 0 cubed plus 0 squared minus 5 times 0 plus 3, and so that had better be 3. So our y-intercept is going to be the ordered pair where your x value is 0 and your y value is 3. Here's a summary of all the information we gathered, and we'll use it to draw a rough sketch of the graph of this function. And I'll start by plotting our x-intercepts and our y-intercept on here. So we have an x-intercept at 1, 0, that's here-ish. We have one at -3, 0, which is roughly here. And we have one at 0, 3 for a y-intercept. And so there are my 3 different points. I'll now refer to my end behavior to have a rough idea of what the ends of my graphs are doing. So off to the right, my end should be going up, and off to the left, my end should be going down. So here's an end going up to the right, and an end going down to the left. And remember, we're just trying to get a rough sketch, so it's okay if this isn't completely perfect. I will then pull this together with this information regarding my x-intercepts in order to get a complete graph. So we're supposed to touch and turn at the x-intercept 1, 0. That means that this end is going to come down. It has to hit this x-intercept, but it's not allowed to cross through the x-axis at that point. So we're just going to turn around at that particular point. We're going to have to turn around and hit this y-intercept up here. And so here is not exactly a perfect graph, but we get the general idea of what's happening. Maybe I'll try to sketch that in a little bit better for us. Going to turn around, make it look a little bit smoother. We have to hit the y-intercept because we're supposed to cross through that point. After that, let's see what happens at our other x-intercept. We're going to have to turn around somewhere and cross through that as well. And we do go directly through the x-axis at that point. So we're going to chop straight through, and that is going to allow us to meet up with our other end. And this gives us a very, very, very rough sketch of what the graph of this particular polynomial might look like. Now, if you wanted to do a slightly better job, of course you could plug in more ordered pairs, or more x values rather, to this original function in order to get more ordered pairs. So for instance, if you wanted to take an x value of 2, you could plop it in here and see what you get and then plot that ordered pair. You could plop in, say, -1, -2, again, see what those ordered pairs are, and it would make this sketch a lot more accurate. But what we've done here is given the basic shape of this particular polynomial function, and all of our 3 intercepts here are completely accurate, as is our ends and our behavior at each of our x-intercepts. So there we go. Here is the extra example of graphing a polynomial.